Hi and welcome. So now it's time to build our first machine learning model in this class. And we're going to build this model to classify a 3-class data set. So it's 3 species of iris flowers. And this iris data set's actually very famous in the history of statistics and machine learning. It goes back, believe it or not, into the 1930s when it was originally collected. So let's have a look at my screen here and I'll show you the steps. Basically, we're going to go through a workflow of how you do a machine learning model using Python and scikit-learn package of Python. So first thing you should always do when building a machine learning model is have a look at the data. So we're going to load this data set and we'll have a look, we'll give it some column names so we can. So there's 4 characteristics of these flowers that we'll use to classify them. Basically the sepal length and width and the petal length and width. Sepals are part of the flower structure. So we're going to go ahead and run that, and we've loaded the data, and you can see we've got the length and width for sepals and petals, and we have a species name, Setosa. And we can also look at the types of data. And fortunately for us, to make this easy, this demo easy, these 4 features, which are the sepal and petal lengths and widths, are already floating point numbers. So we don't need to do any change there. And we can do a quick count here and look at the these categories that we're trying to classify by cases. And we're again in luck. There's exactly 50 of each of these 3 species of iris flowers that we're trying to classify. So we don't have to worry about any class imbalance here. In this code, I'm just using some matplotlib and Seaborn package. So I'm using the lmplot method from Seaborn to make a nice plot. And we'll look at 2 different views here of these flower data. So this is just, so we're going to look at petal width versus sepal length and sepal width versus sepal length. And there's other possible views here, of course. But the main thing to notice is that, for example, Setosa, which is in blue here, seems to be pretty well separated from the other 2 species. And the other 2 species, the versicolor and virginica, have some overlap. And so we may expect some errors when we build a classifying model. So next we have to prepare the data set. And this is simple in this case because it's a very simple problem, but keep in mind you always have to do proper preparation of your data set or you're not going to get good results with machine learning. So for the numerical columns here, which I'm calling num columns, I'm going to just use the scale from the scikit-learn pre-processing package. And I'm just going to scale the whole data set at once. Normally we'd split it and then scale, but in this case, for simplicity, we're just going to go ahead and scale, and we're going to rebuild a data frame, and we're going to run the describe method on that data frame so we can get a little feel for this. So you see there's 150 cases in each case. But what I want to call your attention to is, for example, the standard deviation now is pretty much 1 all the way across because we've scaled these data. And the mean in every case is essentially 0. So we call this mean, demeaned, and variance scaled data. So now each of these features have the same numeric range of values, and so one isn't going to dominate another in training our model, creating bias just because the numerical range is different. Now there's one other issue with this data set, that scikit-learn cannot deal with categorical variables for classification. It needs numeric. And in fact, it's the case that scikit-learn can only deal with numeric NumPy arrays, okay? So we got to transform them. So I've built this dictionary here where I'm going to assign my keys are Sentosa, Versicolor, Virginica, and I'm going to assign them numbers 0, 1, 2. And I simply do that in this easy list comprehension here, and we'll have a look at what I get. And you can see, well, the first 5 rows here are all Sentosa, so they all have 0 as their species code. So, one last preparation step before we actually get to train and test the model. I know it seems like a lot of prep, but prep is key to success here. We have to split the model. We don't want to have bias because in our evaluation, if you trained a model and evaluated a model with the same data, you'd get overly optimistic results because you're using a biased evaluation data set. So what we have to do is we'll split. In scikit-learn, the model selection package within scikit-learn has this train test split function, and basically we just split the data set, and we're going to create a training set of features, a training set of labels, and a test set of features and a test set of labels. And we're going to exactly split this data. So we're going to Bernoulli or randomly sample this data. So we're going to have 75 cases in our test data, 75 cases in our training data. And there's one other trick here. We want a one-dimensional NumPy array, so we have to use NumPy ravel on this result here, where we take the column, or else we wind up with a two-dimensional NumPy array, which is going to cause things to break. So, and we'll print the shape of each of those resulting NumPy arrays. So you see it's 75 by 4, because we have 4 features, 75 by nothing, because we have 1 label for training, 75 by 4, because we have 4 features we're going to use for test, and 75 by nothing, because we have 75 labels we'll use for testing. All right. So now we're finally ready to build a machine learning model here. And you can see from scikit-learn.neighbors, we're going to import the kneighbors classifier. And so there's always 2 steps in training a scikit-learn model. The first step is this one here, where you define a model object, and I'm calling it KNN underbar model. And in this is where you can give arguments or hyperparameters for the model object. So in this case, we're going to do, our number of neighbors is going to be 3. So I just say that here. I'm not going to give any other hyperparameters in this demo. Then we fit the model with a fit method. You see there's a fit method, and we give it the training features as a NumPy array and the training labels as a NumPy array. Okay, let me run that. And you'll see what you get back is, if you don't assign this to anything else, you get back this little printout, and it says, it tells you what you're doing. It says the distance we're using is the Minkowski distance, which is basically not different from the Euclidean. And so you can see the one hyperparameter I set was the number of neighbors was 3, etc. And we're not doing any fancy weighting here. We're just taking a majority vote of the 3 nearest neighbors. So now we have to test our model, and we have this test data set. So we're creating a data frame here because we want to do some nice graphics. We're going to put our test features into a data frame. We're going to add to that data frame a column we're calling predicted, and I compute that using this predict method on our model object and the test features. So the test features are the argument. It's a NumPy array. Predicts what the scores should be based on the training we just did for that model. So the only other thing I need to do is determine whether it's correct or not. So how do I do that? Well, I've got this list comprehension, and so I zip up predicted and the actual label values. And so I'm using zip, and then I've got X and Z here. So I say it's 1 if X equals Z. That is, I've correctly classified the case. The predicted is equal to the label, or 0 otherwise. And then I'm just going to compute an accuracy metric here. In other lessons, we'll go into more detail of evaluating classifier models. But in this case, we're just going to compute accuracy, which is just the number we get correct over the total number of cases. So that's very simple, times 100, so it'll come out in percent. And I'll just print that. We get 96% accuracy. Well, that's pretty good, given that we've done very little work, albeit on an easy problem. How good or bad that is, given how easy the problem is certainly up to debate, but it seems pretty good for a first try at that. And so there's one other thing we can do, which is we can also create those plots again and see what that overlap, what those errors look like. And on my screen here, I have code to do just that. I have, so how does this code work? So first off, we have to go back the other way. So we're going to recode 0 as the key, be Sentosa, 1 is versicolor, 2 is Virgidica. And so that's our species. So now we give the species something human readable. And I'm going to use 2 different markers. And those markers, I'm going to use like a little triangle and a circle. And so triangles for correctly classified cases, circle for errors. And then we're going to use the same color scheme we had before. And you can see with Seaborn, I can set a marker type here. I get the columns. I get the colors. And we'll talk about the details of Seaborn in another lesson. So don't worry about those details too much just now. But let's go ahead and make this plot. And recall that the triangles are correctly classified. So here we have Setosa, and our Virgidica and versicolor are here. And so you start to see misclassified cases, these circles. So there's a couple here and one here. And there they are, a circle and some other circles. So generally we did pretty well. You can see there's a decision boundary somewhere running through here, for example, which the k-means classifier is using, the k equals 3 k-means classifier is using to determine which class to put that flower species in. And that's when you're close to the boundary and have some overlap, that's why we have some errors. So I hope that gives you an overview of how we can use scikit-learn to train a classifier model and evaluate it. So what were the steps? We prepared the data, which included some recoding, scaling, and splitting. Then we trained the model on a training data set. We evaluated the model on the test data set, and we made some plots so we could see where the errors were.